these things for real in a moment, but we need to know that the halogens are the elements in group 7. They've got seven electrons in their outer shell. We're talking about fluorine, chlorine, bromine and iodine. We reminded ourselves that, of course, they're simple covalent. So we can use the word molecules, therefore, which simple covalent is the only time we can use the word molecules. So they've got strong covalent bonds between the atoms, which is a shared pair of electrons. Whoops, that's a really bad picture. Never mind. I'll start again. And that's a single bond, so you get something like fluorine. They'll all be the same sort of thing, but they've got weak forces between the molecules, so they've got weak intermolecular forces, like any simple covalent substance, and therefore they've got low boiling points. Do you see how the last topic, or the last two topics, link directly to the level of knowledge builds up as you go along? We learned atomic structure, we learned bonding, we learned properties of substances based on their bonding, and that feeds into this topic. So we've got the halogens there. I need you to know some detail. I'd like you to know that fluorine's a yellow gas. I'd like you to know that chlorine's a green gas. I particularly want you to notice that they're all coloured. They've got this thing in common. We're showing again that elements from the same periodic table have similar properties. Bromine's a brown liquid. It's kind of an orange solution when you dissolve it. When it's in aqueous solution. Bromine water we call it, but that kind of brown liquid is vaporizing at room temperature. You can see the vapor hovering above it. An iodine is a grey solid, but it's a very low melting point solid. When you heat it up just a little bit, as I'll show you shortly, it goes to a purple gas. Okay. So they're the kind of basic. If you look at the pictures, we'll have a look at the halogens as we go along. Okay, so there's an extra detail here, which is something we've not talked about yet, which is the boiling point increases down the group. Boiling, I can't remember the word boiling. Boiling point, or if you like, melting point, increases down the group. And this trend continues beyond iodine, not that we need to know about elements beyond iodine. So they get darker, as someone pointed out, but the boiling point also increases down the group. So do you think those intermolecular forces gradually get bigger, go down the group, or gradually get smaller? Do you think they get bigger, point up? Do you think they get smaller, point down? The intermolecular forces that you've got to overcome, are they getting stronger, or are they getting weaker? Yeah, they're getting stronger. Which means that the intermolecular forces are still weak. Intermolecular increase in strength. The reason for this, we'll come back to in another topic, is as the molecules get larger. So as a general rule, we'll explore this more in Key Stage 5 if we do it, the larger the molecule, the greater the intermolecular forces, the higher the melting and boiling points. And that becomes important in other topics too, so we'll come back to that. So halogens are quite reactive, and we need to know about some of the reactions of them. We're going to investigate some of those together in a moment. I think most of this is reasonably intuitive, but it's useful to know what you need to know. But if I asked you what happens if we react H2 gas with a halogen like Cl2, but it could be Br2, it could be F2, it could be any of them, we would get HCl, which we know is an acidic gas. Okay, we know that HCl is an acid. So that's the first thing you need to be aware of, that they react. We'll learn about the order of reactivity and later on. They also react with metals. So let's say they might react with something like, and I told you this when we did the alkali metals, they react with something like sodium, but other metals too, in the same way. What would that produce? I think you could discuss that now. So react with metals, so metal plus halogens would give you the metal halide. The name changes as the chlorine goes from being an element to being a compound, sodium chloride. But what we're going to look at, and we'll do this practically first, and then we'll write it up, is we're going to look at some important reactions of halogens. So the next reaction of halogens you need to know about is definitely more complex, and maybe showing you before doing the practical, even though that wasn't the original plan, is probably for the best. Now, you might well have seen this before, you might not have done, but we're going to just write it up as if you've seen nothing. I'll explain it hopefully as we go. But we're going to talk about the displacement reactions of halogens and halides. So let's be really clear first of all what I mean by halogen. By halogen I mean Cl2, Br2 and I2. And by halide I mean chloride, bromide and iodide. It will make no sense, any of this, unless you're clear in your head what we mean by those substances there. And we're going to learn, we'll talk about what this looks like when we get to the practical side of it, but we're going to learn that we can use displacement reactions to determine the order of reactivity of the halogens. So I'll write that down and you can catch up. So we can use these reactions to determine something called the order of reactivity. Find out which is the most reactive out of the three and which is the least reactive out of the three. Right, so a displacement reaction, if we just think of it as swapping a more reactive element, well actually I'm going to reword that, is when a more reactive element swaps out, or further word displaces, even though that's part of the definition, but so swaps out or displaces a less reactive element from a compound. And you've seen this before, you've seen this in Key Stage 3, this is not a new idea for you. And I'll give you an example here of what we mean. So rather than give you an abstract example, I'm going to give you an actual example that we're talking about. So you've got to decide in this example, which is the element, which is the halogen, which is the halide, it's meant to be AQ, that was a mistake. Which is the more reactive halogen and which is the less reactive halogen in this example. Sorry about squeezing that in there. So have a little think about that reaction, if you can read it okay. So we've got chlorine, which is aqueous, sodium bromide aqueous goes to bromine aqueous, and sodium chloride aqueous. Which is the halogen, which is the halide, or which one's a halogen, which one's a halides, which is more reactive out of the elements there. So here, most of you spotted that out of these two, chlorine and bromine, chlorine is the more reactive because it is displacing bromine from sodium bromide. Let's write that down then. So more reactive as chlorine displaces bromine from NaBr. We need to know why it's more reactive, which we'll come to later on. We need to know how we know this reaction has taken place. So there's quite a lot going on in this. I spread this over a couple of lessons, and we'll take our time with it. But chlorine is more reactive because it will displace bromine from sodium bromide. Right? We're going to do the same thing, just so that you see the pattern here. But chlorine will also displace. So chlorine will displace iodine from sodium iodide. So more reactive. So out of those three elements, chlorine and bromine and iodine, chlorine's clearly the most reactive one. So you might be able to predict out of bromine and iodine which one of those is the more reactive just by looking at the periodic table. So have a look at that now, I think. So you spotted that bromine will do the same thing, the same reaction. Aqueous bromine that we call bromine water will displace iodine from sodium iodide. So these reactions are all the same, just the more reactive displaces the less reactive. And we might have spotted that the trend of reactivity is the other way round to the trend in reactivity of the alkali metals we were discussing at the start of the lesson. And so if we look at a periodic table, a sort of sketch of a periodic table like that, down this group here they become more reactive. Down group 1, but down group 7 they're more reactive going up the group. They get more reactive up the group, and so you just make a little sketch of that on group 7, they get more reactive. And although it's only group 1 and 7 really that we study, that trend is the same for group 2 and the same for group 6. Those patterns follow, and there's a reason why they follow, and we'll think about the reasons why as we kind of go along. Okay? I'm going to talk you through the practical investigation now that you can do to show this reactivity. In order to do the practical, we need to know a couple of things first. I'm going to write those down, then I'm going to set up the best I can. We'll do it next time. But you need to know that we're going to use aqueous chlorine, which is called chlorine water. Just slightly coloured, very pale green colour. Aqueous iodine, which is brown solution. So they get gradually darker, as someone pointed out earlier on. And KCl, or sodium, I'm not sure if it's potassium or sodium chloride, doesn't matter. Let's stick to sodium chloride. Sodium chloride, sodium bromide, and sodium iodide are all colourless. No colour at all. So I'll give you a chance to write that down, and I'll show you what we're going to do next time. Keep this going. So we're going to have a well plate like this, and we're going to sketch what this looks like and think about what we're going to see in each of the possible combinations of reactions here. Okay, so we've got, if we draw this, so if we write here, like so, there are 6 reactions. We're going to have a grid like that, and in each box we're going to say whether there's a reaction happening or not. So there's no point reacting chlorine with sodium chloride, bromine with sodium bromide, or iodine with sodium iodide. We just don't do those reactions. We're left with 6 wells, 6 reactions that we can do to determine whether they react or not. I've already told you what the outcome is in each case, and we can show that with a tick and a cross. And so, will chlorine react with sodium bromide, yes or no? From what I've told you so far. Will it, yes or no? Will chlorine react with sodium bromide? 3, 2, 1. Yeah, fine. Will chlorine react with sodium iodide? 3, 2, 1. Yeah. And will bromine react with sodium iodide? In 3, 2, 1. Yeah. We said no there. Yeah, okay. So bromine's higher up the periodic table, so it's more reactive than iodine. And we'll talk about why later on. So those 3 reactions go, and then you might have spotted already that these 3 don't go. But how will we know? We've already written the balanced equations for each of those. We know how they go, and these won't go. We'll talk about the reasons why. But how will you be able to tell from doing the reaction? So we've got to think about those colours. So this is pale green, this is orange, and this is brown. What I'm going to do is pause a sec, let everyone get up with me, and then we'll talk about it together. So all of the top ones are colourless. Chlorine solution is pale green, bromine water's orange, iodine in the solution is brown. So we've said here we've got a pale green solution, almost looks like water, and all of these are colourless, almost look like water. So, but we get from chlorine and sodium bromide, we produce bromine, and we know that bromine is orange. So this one we know, if I put a little note, number 1, it goes from colourless to orange, and that's the production, or let's say colourless, or pale green I should say, pale green or almost colourless, to distinctly kind of orange colour, but it's the production of the orange that tells us we've made bromine, tells us the reaction's gone ahead. Number 2 is exactly the same sort of idea, so pale green. This time, instead of going orange, we're generating iodine, so we're going to generate the iodine solution, which is brown. So we're going to get a distinct colour change. And number 3 here, we've got this orange colour of bromine water, and that's going to go brown. So in each case they get darker in colour because you're generating a halogen which is darker in colour than the one you started with. And in these 3 cases, it's not always easy to see whether anything's happened, but in each case you either see no change, or it's in some cases it looks like it's getting paler in colour because you're just diluting the solution. So over here no change, but over here they get darker every time, and it's very easy to see which ones get darker as long as they don't use too much stuff. Okay. But to link back with what we were doing just at the start again, number 1 there, this was number 1, so the chlorine reacting with sodium bromide. Number 2 was this one, and number 3 was this one. So we can write them as balanced equations. So if we just write up here, just to remind ourselves, this is the formation of the orange colour, this is the formation of the brown colour, this is the formation of the brown colour. So in this case, orange to brown. So in each case, they get darker. If I go back down there again, give me a chance to just finish that off. Do that so you hopefully can see all of it. So as a first run through then, and we'll come back to this next time, we're going to be able to explain kind of why the halogens get more reactive as we go down the group. And one way to show that is by looking and comparing how chlorine and fluorine react differently, okay, or why fluorine reacts more quickly. Now this is a simplification, but it helps us to understand what's going on. Now last week when we were talking about the alkali metals, we said they all react by losing an electron to form a 1+ ion. Here, the halogens react by gaining an electron. And that's what we need to say in our answers. React by gaining 1 electron to fill the outer shell, becoming 1- ions like fluoride or chloride. So we've got an electron or we can put E if you like, got to join it, or an electron coming to fill that outer shell. So essentially we've got to think about what is it that means that the electron can attack that, or can go into the outer shell of fluorine more rapidly, more easily than can happen for chlorine. So there is an electrostatic attraction between that nucleus of fluorine and that electron. So don't worry about the note making for a bit. We'll come back to this next time. I want to talk to you about it now, please. So we've got an electrostatic attraction between the positive nucleus of fluorine and the electron, between the positive nucleus of chlorine and the electron. Eyes this way, please. Just listening, thinking, processing. We'll go through it again next time and making a few extra notes if we need to. But it's which one has got the stronger attraction, which electron has got the stronger attraction to which nucleus. So the answer, we know fluorine's more reactive, so for some reason fluorine is more attractive to that electron. The answer is the same arguments as we made last time for the alkali metals, but the other way around. So there's 1 less shell, which means there's less shielding, just as we were doing at the start of the lesson, and then there's also less distance between the incoming electron and the nucleus. So greater attraction, we say, between incoming, this is the word we've got to get in our answer, greater attraction between the incoming electron and the nucleus for fluorine versus chlorine. All right, that's true. It's chlorine more reactive than bromine for the same reason, bromine more reactive than iodine for the same reason. So exactly the opposite answer to the answer we gave for alkali metals, and we do need to practice this, and we will. You've got 2 minutes to write this up, but I'm going to stop the video there.